This time we are going to talk about differentiation rules. We know that there is one definition of the derivative, and it's two concepts put together, very important concepts. The concept of the limit as h approaches 0, and the concept of the difference quotient. So this is f of x plus h minus f of x divided by h. This we know. We're not going to use it again. We will be using it again towards the end of the class, you know, the final exam. So please remember, this is the only definition of the derivative function. But moving forward, we're moving away from this definition. Still keep it in mind. It's two concepts put together. So now differentiation rules, we have several differentiation rules. Now, can anyone remind us, when we had f of x equals the square root of x, we used this definition to find its derivative. So what is the derivative of the square root of x? This is very important and we need to remember it. Anyone remembers?
Was it 1 over x?
Careful.
1/2 x to the negative 1/2.
Yes, but I prefer it like this, 1 over 2 the square root of x. You're right. Everything you said is perfect. But you will see later why I would like you to remember it as this. So we say this. The square root of x prime is 1 over 2 the square root of x. Please remember it like that because we need it later. Okay. So now let's look at the power rule, which is this. I didn't tell you, but we use a definition to find this. It's the same thing. So the power rule definition, differentiation, we're using the power rule, says this. If we have x, when we talk about x, we really mean plane x, okay? I do not mean a function that is, for example, natural log x. This is a function applied to x. No, when we say x, we really mean plane x. If we have just plane x to a power n, so remember, I always tell you, because it's different, I guess, I got used to it. So this is my n, and 3 bubbles, or hives, or whatever you want to call it, n and m. It doesn't matter, you can use m, it's the same thing. But if we want to differentiate x to power n, the rule says this: bring n in front, whatever it is, and subtract 1 from the power. So, for example, if we have x to the 3rd power prime, can anyone give us the answer?
It's 3x squared.
Very good. Now, remember we had, and I always like to combine and go back and refer back to, I'm just logging into WebAssign with my, done. So, because I want to share my screen in a second. So, remember when we looked at limit laws, so when we had a limit, let's say, of a function f of x, which is, let's say, a poly. As x approaches a, we said, oh, this is nothing else but f of a. Also, we looked at another limit law. And the limit law was limit of a constant times f of x as x approaches a. Let's assume this is a constant, it's a factor, and this is still a polynomial function. How do I find this limit? Anyone remembers the limit law? It's a very important one.
You find the limit of f of x as approaching a, and then you multiply it by c.
Yes, so it's c times f of a. Perfect. Because I was looking at the same setup. And you can say, what do you want with this? Here's what I want with this. Now, I would like to ask, how much is 3x to the 4th power prime? the same idea.
Isn't it, wouldn't you multiply 3 and 4 and then
Exactly.
it would be 12x
Yes,
cubed?
the same, pretty much the same idea. So the constant stays, and I do my thing for the function, and I have to multiply by 3. Perfect. That's the basic idea. Yes. So what do I get as the answer? Awesome. Anyone? It's okay if you're wrong.
It's 12x cubed.
Yes, it's 12x cubed. 4 times 3 is 12. I have to bring 4 down, but I have to multiply by 3. So I get 12, and I have to subtract 1 from the power. Awesome. Okay, so this is the power rule. I would like us to look at a few examples. And of course, the other rules would be, if I have, it's the same idea. Remember, we had the limit of a function plus another function as x approaches a. This is not the distributive law, but this is exactly the same with the limit of f plus the limit of g as x approaches a. Under certain conditions, what were the conditions in which I was allowed to do this? What conditions? What has to happen?
The limits.
Yes?
The limits existing for each.
Exactly. These two are both numbers. They can be the same. They can be both 0. We don't care. But there are two numbers, potentially the same, that can happen. And then I can split the function, the limit. So then what will you say when we have to add or subtract two functions and we want to differentiate? It's basically the same rule. That's why I always try to go back and connect the concept, so it's easier for you to remember.
The derivatives have to exist for each.
No. Here, of course, yes, you're right. The conditions, I didn't even write the conditions because here, of course, the functions have to be differentiable. I completely agree. So here the condition was both limits have to exist, a number. Here the same thing, functions have to be differentiable. But because we are looking at abstract situations, we have to assume that when we look at the rule, we expected them both to be differentiable. So all I was looking for is this. Same idea. So if we add and subtract functions, yes, that are differentiable, then because we are not evaluating, so we really don't need to discuss that at this point. But you're right, they have to be differentiable. So when we add or subtract, and we want to differentiate the sum or the difference, it's the same thing. We can differentiate separately and then just add or subtract, depending on what the problem is asking us to do. Okay, I want to discuss one function that I would like you to, so start making a list. Start making a list with all these derivatives. So this should be on your list, this should be on your list, the power rule should be on your list so far. Okay? Okay, somewhere on a little notebook or separate, somewhere. Okay. I want to talk about one function, though, that is the exponential function, e to the x. Yes, you may know what the derivative of this function is, but I would like to look at how we determine that. It's not crucial. I can simply give you the formula, but I think it's a good idea to look. It's up to you. I let you decide. If you want to see how this is obtained, then we will have to look at the definition. I just mentioned that we're not going to use it again unless we want to prove something. But in this chapter, we're going to base all our calculations on differentiation rules. So if we want to look at that, then we will have the limit as h approaches 0 from e to x plus h minus e to x divided by h. If you're curious to see how, I'm not going to test you on this. If you're curious to see how we get a derivative of this function, I will proceed. If you say, maybe, maybe not, you want to think about it, or you don't want to see how it's done, it's fine too. Any Any idea?
Yeah, I'm curious. Yeah, I do want to see.
Awesome, perfect. So we want to determine the derivative. We want to see how we find the derivative of e to the x. So we are in search of e to the x prime. So that's why I put f of x plus h minus f of x divided by h. I want to talk about this power or exponential notation. So remember, e to x plus h is the same with e to x multiplied by e to h. How do we know? Well, if I'm given e to x times e to h, I copy the base and I add the exponents. So I always like my students to know that this is, if you want, a dynamic relationship. This can be changed into this and this can be changed into this. I need this form here. I can't proceed without changing this expression into this expression. So, therefore, you know me, I'm not going to copy it. I jump over here, so you continue, find the circle, and you continue. So, remember, we do not drop the limit operator because we have not applied it yet. I will replace e to x plus h by e to x times e to h, and minus e to x divided by h. Now look at the numerator and say, I think I know what you are going to do next. What would you say? What will I have to do next? When you look at the numerator. Any ideas? Remember, every time, yes, sorry. Say it again.
The e to the x, they cancel each other out.
I cannot. But I can do something else to e to the x, but I cannot cancel it. I would have canceled it if I had e to the x minus e to the x, yes, but not in this form. But yes, I am going to factor it out. Since it does not depend on the variable, e to the x has nothing to do with age. The variable for us is age, not x. So e to the x can go completely outside of the limit. So then I have e to the h minus 1 divided by h. At this point, we need to talk about this. Very soon, one of your colleagues already asked last week, what about L'Hopital's rule? Yes, I will introduce it after we look at some differentiation rules, then I will talk about L'Hopital's rule, I promise. But we don't know it right now. So what I can do is, for this, look at TI-84, just to see what happens here. Where is this piece going? Because, of course, when I plug in age equals 0, I get 1 minus 1 over 0. So I have to get 0 over 0. This is the difference quotient, right? The limit of the difference quotient. It has to be 0 over 0. So let's take a look. I'm going to put this function in the graphing calculator. I cannot use h. The calculator doesn't have h. So I'll have to use x. But this is not this x. It's this. X, 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 right? So let me share my screen. Okay, here it is. So in y equals, just plug in, remove anything and everything from there. And just plug in. Do not forget parentheses. So we need e to power x. It should be h, but I don't have h in the calculator. Minus 1. And divide by h. Of course, I don't have h in the calculator, so I have to use x. So I want to go from left and right of 0. I cannot put in 0. The calculator will scream at me saying, what are you doing? But I can put left and right of 0, very close. 0.1, negative 0.1, and now I want to go even closer. I want to go to 0.00001. I want to go to negative 0.00001. What do you think this limit is? And before you say anything, let's look at the graph of this function. So I'm going to look at the viewing window. I only need around 0. So I'm gonna say, okay, from -2 to +2. And let's say from -4 to +4. That's all I care about. That's not what I meant. With a scale of 1. -4 to +4 with a scale of 1. So let's see. Okay? So we know that this function is not defined here. We know that, because I plugged in 0. I plugged in 0 and it screamed at me. So what you see is deceiving, right? But we know it must be an open point here. Okay, so back to the table, or the graph, it doesn't matter. What will you say this limit is? Which is this limit. All this. What is it?
1.
Exactly. So look how nice this is. This is the nicest function of all. We will encounter, there are other functions whose derivative is the same with the function. So the rate of change of this function is the same with the function itself. So that is the explanation. I wanted you to see this because it goes back and forth. And I wanted you to remember this, hopefully easier, saying that e to the x prime is e to the x. Okay, and now I'll open the floor for any questions, and we're going to the book, and we're starting here. Okay, so this is section 3.1, and we want to look at any function to differentiate from 3 to 34, and then we'll look at more. I would like to be the first one to choose, and then you choose. Okay, I would like to start with a weird one, like 21. It looks weird. Then you choose the next one. So 21 is y equals 3 e to the x plus 4 over, I think it's the cube root. Is it the cube root? The computer is so far away from me, but I can look in the book. I see it as the cube root. Do you see anything else?
No, cube root.
Okay, perfect. Okay. So we have here two functions.